Good evening and welcome everybody, this is Obi-Wan Pitts. We're in Simplex Pachinko. Sorry about the zero timer there for a bit. No worries. Math Dork, welcome back. Good luck with your phone updates. I'm sure you're already gone. So I know that we'll probably get back to this at some point, but I know that a lot of times engaging in mental work is often not very much appreciated by people who did not get into mental work themselves. My father's very hands-on, but at the same time, like, he was originally planning on going into, I think, engineering. He had a drafting ruler that had like the 3 different sides to it that like has, you know, 6 different measuring styles or whatever, you know, tenths versus the 16ths and whatever versus metric. It just, yeah, there was a lot. And and he's also like an accomplished woodworker. We had talked a bit about this because he wanted to make that thing that kind of looked like a fidget spinner that we did here on the channel a couple months ago. Oh, man. We apparently got a partial block on something. What happened? No, what that? Come on, man. Contains copyrighted material. Alright, look, I thought we fixed this. Oh, alright, pen. Turns out. Alright, we will erase the song while we keep everything else exactly the same. So hey, pen, turns out the blurb that we use for your thing ends up causing some problems with copyright. Oh no. That's alright. We'll pass on that one. Anyway. So, tonight we're going to work on GRE. Tonight is night 14. Math help. Nope. Nope. Questions. By request. Ah, there it is. April. So we did this at the very end of April / like May 5th. We might have bled a little bit into that. So anyway, we will have more of that stuff put onto YouTube when I can get to it. Okay. So for tonight, we were looking at Peter Liljedahl's uh, last class. Last stream, we were looking at Peter Liljedahl's Building Thinking Classrooms for K-12 specifically, but as I was a community college professor, it ended up working out really well for most of my classes as well. So we will continue to talk about this on Mondays until we get it done. So let's go. But for now, we have our GRE math subject test, which currently we are on Calculus 1, trying to explain how what is this? Not continuity. Limits. How limits work, and then eventually we get to continuity, and then the definition of derivative. So, there's a few different ways that we can go about this. I think we did actually look at the first example last time that we did this. So, I said that
anytime, anywhere. Got a show of your own? Upload your video to Spotify. Turn views into fans and monetize your passion.
Right, limits of functions at infinity. What we would like to do here is say that okay. So f of x is going to go to some limiting value. We call it m. Typically, yeah, maybe they're saving L for the x values. A lot of times we'll see capital L for the function limits, and then just like a, lowercase a, for our x values at which these limits occur. In this particular case, we're saying that f of x is going to go to m, or approach m, as x approaches infinity if, for every tiny number epsilon that we can find, which is still greater than 0, there exists some delta for which x being greater than that delta is going to mean that f of x is going to be less than that epsilon away from our m value. So in this particular case, we could also draw this. Let's maybe use the line tool, because, you know, that's what it's meant for. Alright, so we say, nope. Dotted? Cool. Excellent. this is going to be y equals m. We're going to have our function. Let's just come up with a completely random. Don't know what kind of function this could possibly be. Kind of function that looks like this. And in fact, let's make this maybe a little more obvious. Alright, something that does that. And you know what? Let's even like even not make it what one would assume it is on the other side. Let's make it a little more unpredictable. Okay, it's a little bit weirder, but nonetheless, same deal. So here, what we're saying is that we can find some epsilon such that after, in this case, we're just labeling it as delta entirely. Okay, so for this particular diagram, what we're saying is that if this limit exists, so if f of x is truly approaching this limiting value m as x goes off to infinity, then any epsilon we could possibly imagine. So you want it to be 1. This is probably approximately 1 on whatever scale this might be. So we just say, all right, if epsilon is 1, in this particular case, we can find a delta, which is marked there, such that our function f of x will always, from that point on, always be within the, that's not green. It's like salmon, whatever. Alright, so f of x will always be within this salmon-colored bound from that point delta on to infinity. Now, if the limit m truly is a limit, then we could always pick some epsilon and then go to the graph and find whatever delta is corresponding with it. Find the largest of such deltas, just in case this like oscillates and comes back. There will always be some largest delta, after which the function will always be within that salmon-colored bound again. And pick a different epsilon, make it, 1 times 10 to the negative 15th. Then we can go as far over as we want and eventually find that intersection point where it goes through y equals m plus epsilon or y equals m minus epsilon. And that delta where it crosses will be there will exist a largest such delta, such that the green function will always be within that salmon-colored bound from that point on. Right? And then again, pick a different one, 10 to the negative 5 millionth, and then it will work again. We can always find some value, delta, such that there is a highest delta where the function is always within the bound. It's just one of those like cool things that exist, and maybe you don't really get told much about it or don't recognize it immediately. There's also the possibility that your definition may not be quite as rigorous as like the true definition, so just be careful that if your definition isn't quite the same, there may be some issue with it or some like nuance in a formal definition that is not in your kind of common definition. It always makes an interesting issue. And if you're planning on being like a mathematician, then oftentimes it becomes like spot the difference, where you end up saying, okay, why doesn't this other definition work? Like, let's try to break it and see what happens. Right, and we can always do the same for negative infinity as well. We just have to reverse this and say that, you know, f of x is going to approach some m value, whatever that is, in the opposite direction. In the book they say, let's do a lowercase m instead. It doesn't matter, right? Capital N instead of m, sure, that works too, as x goes to negative infinity. If, for every epsilon greater than 0, there exists some delta less than 0, such that x is going to be x is less than delta implies that the distance between f of x and n is going to be less than epsilon. This was for all epsilon greater than 0. There exists some delta less than 0, such that x is less than delta implies that distance between f of x and n is less than epsilon. Right, so actually I need to do this a little better. F of x goes to n as x goes to negative infinity. We need to state out here that this is an alternative to the above. Okay, so in these examples, we have limit as, that's not my standard color scheme. Okay, limit as x goes to positive infinity of 2x squared minus x plus 1 over x squared plus 4. B. Limit as x goes to positive infinity of 2x squared minus x plus 1 over x cubed plus 4. C limit as x goes to negative infinity of arctan of x, and D limit x goes to 0 of 1 over x. That is not actually described in the above. So, I mean, fair play here. Come on now. It's not like it's an issue. Yeah, we described last time the approaches from one side or the other in order to make sure that we get a one-sided limit as well as doing the two-sided limits. So... for something like this, I know what way I would want to do this. Right? If I'm going to infinity, I can't just plug stuff in. So, again, standard. Plug in. Well, in this particular case, we get something that is, 2 times infinity squared minus infinity plus 1. The plus 1 probably isn't going to do anything here. Alright, this is going to be infinity squared plus 4. The plus 4 on the bottom is really not going to do anything either. And when you square infinity, you also get infinity. So this becomes a bit of a problem. We could show right, 2x squared is always going to be greater than x, and therefore 2x squared minus x is greater than 0 for all x greater than some value delta, right? We can go ahead and do that.
There's more to Spotify than meets the ear.
Realistically, we don't really need to do it,
With over 300,000 video shows and 300 million users already watching
for real,
with seamless switching between
because we can kind of think our way through this. So we could show that this is true, but then we've got the problem of, well, this is going to be infinity over infinity,
views into fans and monetize your passion.
right? And this is a problem because depending on how big the infinities are, we could get that infinity over infinity could be could be less than 1 and going to 0. So if we have a big number on the denominator and a smaller number in the numerator, significantly so, then this ratio could go off to 0. We could also have something that is equal to 1, and then, right, or even equal to just a, some constant. Right, so this one could be greater than 1 going to a, right? Or we could have one that just goes to infinity altogether. Right, numerator and denominator being positive. Right, this is an upward-facing parabola divided by another upward-facing parabola. So we're never going to end up getting negative numbers as we go off to the infinities, either one of them. So, having all these different possibilities here is what is called indeterminate. Because there's no way to tell immediately. There is a way to tell with experience, but there is not a way to tell immediately which of those 4 behaviors you're going to have with this particular problem. So my favorite way of doing this is we say, okay, look, we're going to take the limit as x goes to infinity of these things. So this is going to be, we're going to multiply both top and bottom by the highest degree term that we have. So just the x's, we don't need the 2 in there as well. But what we do is we say we're going to divide the top, or we're going to multiply the top going across by 1 over x squared. Right, so this is going to be 2 minus, this is x times 1 over x squared, so this is going to be 1 over x, and then plus 1 over x squared. And in the denominator we get x squared times 1 over x squared, which is 1, plus 4 over x squared. Alright, and then here we say that as x goes to infinity, all of these things with x's in the denominators are going to go to 0. So we end up with, on the top, a 2 minus 1 over infinity is going to be 0, plus 1 over infinity squared is also going to be 0, divided by 1 plus 4 over infinity squared, also 0. So here we end up getting a value of 2, which is going to be the limit for x goes to infinity of 2x squared minus x plus 1 over x squared plus 4. Do we need to do all of that work? Well, you know, it's nice to do it the first few times that you see this, especially if you're doing a definition of limits. But most of you probably know the shortcut here, and that is in pre-calc, we teach the students to look for the highest degree term that exists in the numerator and denominator. And then you're basically just finding the ratio between them. It's 2x squared over x squared, and that's also 2. Or just the ratio of the highest degree coefficients, provided that they are equal. I also kind of like this one, because if they're not the same, you can actually tell what's going on. Right, so this is going to be approximately equal to the limit as x goes to infinity of 2x squared over x squared, which is 2. Again, if they're not equal, it makes it kind of interesting, because now we can actually just take the ratio of the individual terms of the lead term and take their ratio and show what it is going to be equal to. So I think that's actually part B. Yeah. What's up with this one? Well, we could do the same thing. So here we can multiply by 1 over x cubed. And we end up with the limit as x goes to infinity of, here we have 2x squared over x cubed is going to be 2 over x minus x over x cubed is going to be 1 over x squared plus 1. In the denominator, we get x cubed divided by x cubed is 1 plus 4 over x cubed. Okay, and then again, take those limits. So the 1 here, that's not a 1. That should be a 1 over x cubed. Right, so in this case, we see that the limit as x goes to infinity is going to be of 2 over x over 1. The other things that are in here can have been already taking the limit factor if you want to. Or take the limit of those things, which end up turning them all to zeros. Now, realistically, it also does it to the first one up top there, too. So we end up with not the limit anymore, because we're doing it. Right? It's a 0 over 1, which is going to just be equal to 0. All right, why does that work? Again, if we fall back on our pre-calculus definition, then what's happening here is we get the limit as x approaches infinity of 2x squared divided by x cubed. Which, no, that's pretty much the same thing we were looking at. Oops. All right, take the ratio of the lead terms in both of the polynomials. So up top we have a quadratic, down at the bottom we have a cubic. Take the limit of their ratios, and we end up with, again, the limit. It's equivalent to the limit as x goes to infinity of 2 over x, which is going to be equal to 0. So again, it's equivalent in terms of the limits, so you can just let that happen. All right, we're going off to infinity here. Next question, right? Can I do the epsilon delta limit proof for all of these things? I don't know, maybe. All right, the limit as x is going to negative infinity of arctan of x. So in this particular case, we're seeing that we could do this a few different ways. So one is, again, if we draw in something like this, goes like that, and then goes like that, right? So this is going to be y equals the arctan of x, and you know, how do we prove or show what the limit is going to be as x goes to negative infinity? Well, there's a few different ways, right? One is that we could come up with a unit circle right, and then say what we want is that our x value, which is the slope, if you remember, the tangent of a particular angle is going to be equal to, this is tangent of theta is equal to, in this case, x. And therefore theta is equal to the arctan of x. So again, x, the value that we get here, the value of the tangent function, is going to be the slope of the terminal side. Of our angle. Right, and if we want a large negative slope, then we're going to need an angle in either of these two locations. And then we're going to be taking this and moving it closer and closer to our vertical axis, which is where we get a vertical line which has an infinite slope. At this point, it's looking at it and saying, well, look, this is either going to negative infinity, or in theory it could be also positive infinity on the other perspective, right? If we were on this side coming this way, this would have a positive and infinitely positive slope. But we're not doing that. We're coming from this direction and moving ever and ever closer to a vertical line. It will have a negative slope, and it will be very large, fairly quickly. So then, where are we getting to? Well, this is vertical. So if this is 0 and also 2 pi, then this is pi over 2, and this is 3 pi over 2. And also, we could then subtract 2 pi from this one, because our arctangent is only going to have valid values between negative pi over 2 and positive pi over 2. So here, this is going to be negative pi over 2. You can't see it. This is going to be negative pi over 2 along this line here. And again, our diagram is showing us that we're getting closer and closer and closer to negative pi over 2 when we're coming from that side. So that's also really important in terms of, like, if we were looking at just the unit circle with no context. If we're going to look at the arctangent function, then going off in the negative direction is not ambiguous. We only have one possible answer here, and it's that dotted line. Where is that? Again, we just saw it over there. We could actually verify using values that we see here that we would end up with negative pi over 2 for the negative side of this particular function. Now there are probably other ways of figuring that out, but this is not really the point, right? The point here is that we are working on getting a quick-ish kind of answer. And again, it's for the GRE graduate record exam. Graduate record exam. And so just knowing where your appropriate domains are for the tangent function, and what the appropriate ranges become when you switch to arctangent, then you're going to know, okay, we can only go from negative pi over 2 to positive pi over 2. We're getting closer and closer to negative pi over 2 if we go closer and closer to vertical, but having a negative slope.
You can tune in anytime, anywhere. Got a show of your own? monetize your passion.
Right. So for this one, as x goes to 0 of 1 over infinity. So this becomes a little more awkward. So if we look at this, we've got a bit of a problem because, first of all, if we draw the graph of the function 1 over x, we've got this nice function here, but it also has a negative side. Right, so what do we do with that? Well, we're going to have to specify which side we want for this. However, since there is no specification here, limit as x goes to 0 from the negative side of 1 over x is going to be, right, as we come from the negative side, we follow this line in and it goes down. It goes down to negative infinity. Okay, and then the limit as x goes to 0 from the positive direction of 1 over x is going to be equal to positive infinity. Again, we come this way, it keeps going up. So since these are not the same, this limit cannot exist. Okay, now can we prove each of these things? Well, sure. Again, pick a particular value that you want, and you can show that we're always going to end up getting something that's we'll always be able to find a function value which is bigger try that again. Hang on. Right, not s, but nonetheless. If we're doing the limit as x goes to infinity from the positive side of 1 over, nope, sorry, x goes to 0 from the positive side of 1 over x. So we know that the limit should be infinite in extent. We just need to switch the language around a little bit. So, first of all, right, f is going to go to infinity as x approaches some particular a value. If for every epsilon greater than 0 there exists a delta also greater than 0 such that right now this is where we reverse everything a little bit. So we're going to have that let's make sure we got the language correct here. So, if for every epsilon greater than 0 there exists a delta greater than 0 such that, right, right, there exists a delta greater than 0 such that x is the distance between x and a is less than delta implies that the distance between that the, well, yeah, okay, the distance between f of x and 0, so absolute value f of x, is going to be greater than epsilon. As we've stated it in multiple other locations. Right. Okay, so this is what we have for this particular example. So what we do, this is going to be a standard tactic that is used in epsilon delta proofs. Epsilon delta proofs often consist of, one, verification via algebra. So what we're going to do is we're going to show that, yes, the relationship will hold. To find the relationship between epsilon and delta. Okay, and part number 2. Formal proof following the same logic, usually in reverse. Alright, a lot of people are like, why would you do this? That's horrible. Don't do that. But honestly, you're not allowed to start at the end of a proof and work backwards, because it doesn't show that the logic actually holds going forwards. So that's why you need 2 parts to an epsilon delta proof, generally speaking. So we have to, for instance, verification, start with the distance between f of x, so this is 1 over x, and 0 is going to be greater than epsilon. Well, so the good news here is that absolute value 1 over x is always going to be positive for values of x that are greater than 0. And again, what we really wanted at the beginning was what's the limit as x goes to 0 from the right hand side, so from the positive side only. Right, we're looking for the limit as x goes to 0 from the positive side of f of x. Right, let's just write out 1 over x. So, the, again, absolute value, the distance between f of x and 0, so f of x minus 0, absolute valued, is going to be greater than epsilon. Then we can break this down as the absolute value of 1 divided by the absolute value of x. Or we could just say literally, yeah, we're just going to end up with 1 over x. Right, this step here, right, x is always positive in this particular setup. So that's greater than epsilon. Then we can do the whole, like, I hate to say cross multiply, but you know what? In this particular case, we're going to multiply the means and extremes theorem, right? So we multiply the means, which are going to be the ones in the middle, so the x at the bottom and the epsilon up top over there, and then we multiply the extremes, the 1 and the 1 from either side there. So we end up with a 1 here greater than x epsilon, and then we say, well, we could divide by epsilon because that's also going to be a positive number. This is going to be 1 over epsilon. It's going to be greater than x. Okay, and then we can also say, well, we want this to be x minus a, so 1 minus epsilon minus a. And then we want the absolute value of both sides, so now the question is, which one is actually going to be bigger, right? X minus a on the bigger side, well, okay, for us, in this particular case, that's going to be 0. So that doesn't really change anything. Right, and in this particular case, x has to be bigger than 0, and 1 over epsilon has to be bigger than 0 because epsilon was bigger than 0.
All of your favorites from the fields. Brought to you by Ray-Ban Meta. Live effortlessly with Ray-Ban Meta glasses. Iconic style meets Meta AI.
When your deodorant has been reduced to a tiny whisper and tries to tell you, I'm running on empty.
So this is going to tell us that if we want to reverse the way that this is, x minus 0 is going to be less than 1 over epsilon, and we're allowed to take the absolute value of both sides in this particular case because both sides are positive. So it doesn't change the relationship between these things.
300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
Okay, so then here we now have that we now have that x minus a, x minus 0 is less than absolute value of 1 minus epsilon. We don't even need the absolute values, so whatever, that's fine. Okay, so we can let 1 over epsilon be equal to delta. And then we must go through the formal proof. Right, so this is 2. Prove if absolute value x minus a is less than some delta, then absolute value f of x is going to be greater than, what do we call it up there? Delta. Or no. Epsilon. Alright, ads are going to start in about 2 minutes. We'll see if we can get this done. Hopefully so. After that, get up, stretch, cycle that water, go grab some snacks, water, coffee, tea, whatever else you need, or something harder. And then we'll be back with more GRE stuff for Calculus 1. Alright, so here, what we're going to do is we're going to let delta be equal to 1 over epsilon. And a is equal to 0. F of x is equal to 1 over x. So with all of that, we have now the absolute value of x minus 0 is going to be less than epsilon, delta, which is 1 over epsilon. Which then, again, we can say, okay, x is always going to be since x is greater than 0, then the absolute value of that stuff is just x less than 1 over epsilon, which means that epsilon is going to be less than 1 over x, which means that the absolute value of 1 over x is going to be greater than, if we read it backwards, epsilon. QED so proved. Okay. We shall return, so I'll see you in just a little bit. Thank you so much, everybody, for coming, and we got about 3 minutes until ad break's over. See you in a bit. Welcome back, everybody. We are going to do a good form, which today is going to be Tai Chi. We learned the remainder of our other form that we were doing. Where are we? Here we go. A face. So we learned the rest of the form that we were dealing with a couple weeks ago. And generally speaking, what we're doing is we're... did I turn that volume down? That's a very good question. Yeah, somewhat. Seems alright. So, what we did is we... in Tai Chi, normally we start just by warming up. Again, using minimal actual movement with our arms to get our arms moving. And then pretty much just using the swaying motion of our body in various forms in order to sustain the motion itself. So essentially right now, all I'm doing is kicking off a little bit with my feet in order to get my arms moving and keep them moving. I'm essentially letting them hang, but it's a little bit more complicated than that. Whatever, it's all good. The idea is that while we're doing this, it's getting some of the fluid inside of all of muscles and things like that kind of moving a bit. It's a little bit of cardio, but not really. We also, when standing straight like this, one of the exercises that we do is what is called bear. So we kind of hug around just a little bit like this, and then we kind of back into where our back our hip into about where our foot is, and then turn, and then push the other way. You get to about here, turn, push the other way, turn, push the other way. It's something to just kind of get the body moving, get used to the typical hip movement. Usually you want to get a crease in the little pocket that's between your hip and leg. So get that crease kind of moving a little bit, and then again back to the other side. Do that, keep going the other way. We want to be more or less feet forward while we're doing this, maybe a little bit less wide, shoulder length approximately, shoulder width approximately. That does also shorten up the amount of space that we're using here. Maybe a little wider. Keep going like this, back and forth. This also allows us to eventually start doing motion where it's the leading hand, but you're going backwards into it, so it's slightly awkward, is coming up and doing a ward off while the other one drops underneath. You keep the hands approximately equal to each other on their positions. I'm doing it too quickly. Okay, so the form in Tai Chi, I forget exactly what the name is, but that's alright. I've done this a few other times, so as we're breathing in, we bring the hands up, push out a bit, and then come back, and then push down as you breathe out. Then from here, we go to the left-hand side, get a ball of energy, step out this way, and then as we're coming up and shifting our weight to this side. We then come up with a ward off in this direction. And the other arm is there for essentially framing. So you want to have your whole body as a frame, just as if you're doing ballroom dancing. And then from here we go a little bit further, 45-degree angle. We want the back foot at approximately a 45-degree angle to the front, otherwise you can't quite get the hip rotation that you need to. So we come up this way, we sink just a little bit further, bring this hand back, move into roll back, which is this way, into push, and then we sink back onto the back leg and then push. Press, sorry, into press, and then the hands come apart, you sink back onto the back leg and then push. From here, bring the right leg, the front leg, back, and we do a what's called split. So this is going to come down this way and then whack into whatever target you have. It can be this way with an open palm, it could be this way with a ridge hand, it could be an actual fist. Very similar to Eskrima when we were doing the forearm strikes. This was allowing the stick to go further and whip out. Here the split is also doing the same thing with your fingers, be it this or that or what have you. Then from here we're taking somebody's arm that's grabbing onto us, we're trapping their arm and getting it off of us, and then going straight back into an elbow. And then we bring the left leg back, disconnect from each other here, and then come forward and do a shoulder. Like shoulder into the person. It might actually be better if your arm is down here, because there's some other stuff going on, which I found out about today. So, and then from here we can go back into nope, ward off, roll back, press, settle, push, drop into a split, and then elbow and shoulder. I also found out today that when you do the shoulder, it's kind of important to let this arm fly as it may, because my instructor directly slapped me. I was like, okay. So yeah, you can get slapped by the hand if you shoulder into it and kind of let the hand fly. That was shall we say, unexpected. It's a bit of a hazard. Okay. So that was the cool thing we did, or that's the like kind of standard thing we did, and then the next form that we learned today was called, I think, Dalu, but I can't be entirely sure about that. So we start with feet more or less together, and then we're going to do what's called, like, a lot of our other movements have been what are called bear movements. They use animals to describe them. So using this motion, again, having one hand then the other doing something, and also moving mostly in orthogonal directions, is like bear. So we were doing tiger today, where basically the first move is coming up over the top. See if I can actually remember this. Left hand is like just kind of basically generally covering center of gravity. we move step diagonal to the left, and then shoulder to the right. We then, again, let this slap down. Let this stay about here. Then we back the right leg up to about here. Turn the left foot 90 degrees so it's facing the opposite, or sideways direction, and then do a split. Or no, do a pluck. So we move this down here. And then when we do that, we go straight back into the tiger. Comes down like this. Slap out like that. Again, come back. Nope. This goes down like that. Then we... Right, then we come back, turn, and pluck. And then we go back and attack. Come down. That. And then come back, turn, and pluck. Step up. I wasn't supposed to do that yet. Then come up and over like that. No, I'm wrong. Pluck. Right, then up, left, slap out. Step back while rotating. And then pluck down. Blah. Step up. Step left, step right. Come up this way and pluck down. So it's going to keep doing all those movements. Oh dear. I appear to have stepped on an art project. I keep telling him not to leave stuff around. So the idea here is that all of these individual movements kind of work into a nice, interesting pattern. He and I were essentially like this the entire time, and this one's much more balletic. Just because you are like, I come up over the top like this and I start attacking him, and then he grabs this and tries to put me into an arm bar. So essentially he takes it like this, I grab onto my elbow to make sure that it can't bend, or sorry, so that it doesn't go straight, so that it stays bent. Step out, and then back over this way and pop him in the groin if he's not paying attention, which he was, fortunately. Right, and then step back, twist, and then pluck down. So in doing this, it also forced us to stay within kind of like a little box, and also try to read each other a little bit better. So attack, get taken into an arm bar, but then we hold it down and don't allow that to happen as we step out, and then shoulder, and then we step back, twist, and go to a pluck, and now we're facing this way to each other, and then I come back and attack again. Prevent that. Yep. Here. Nope. So this is the first day, literally, that I've worked on this form, but it doesn't appear to be terribly difficult. We'll just see how it goes as time goes on. He was pretty happy with the progress I made, but I mean, again, truth be told, it's not difficult. It's only like 4 literal moves. And for most of them, you need a partner. So, probably not doing that too much. Alright, so... we're back. We've just proved an infinite limit. So what happens when we have, you know, our x value is going to 0 and our y value is going off to infinity? Well, this is what we've got. So if x minus a has a distance less than delta, then the distance between f of x, our function value, and 0 is going to always be greater than whatever epsilon we pick. Or going the other way, if we have an epsilon in mind, then we can always find a delta such that the function's higher. So here we were going in order. We said let delta be 1 over epsilon because we found that relationship up here. If that's true, also a can be 0 and f of x is going to be 1 over epsilon. Nope, 1 over x. Then we get the absolute value of x minus 0 is going to be less than 1 over epsilon, which is going to be our choice of a and delta, which are definitely not random choices. We just had to prove those are the choices that would be optimal based on our algebra from above. A is our limiting x value, the place where we're trying to go to, and f of x is going to be our function, and delta is the relationship between the function of epsilon that we found up above. So then the distance between x and 0 is going to be less than 1 over epsilon, is our assumption. Since x is greater than 0 itself, then the absolute value of x minus 0 is always going to be positive, so we could just take it out of the absolute values. It's redundant. X is less than 1 over epsilon, and also we can swap those in location, so epsilon is less than 1 over x. And since, again, 1 over x is always positive, then it's the same as absolute value of 1 over x. So the absolute value of 1 over x is going to be greater than epsilon when we read it the other way, which means that the absolute value of f of x is greater than epsilon, which, again, QED, to be proven. Right, could we also do that for all of these other ones? Yeah, sure, why not? So this one is that the... let's think about this again. So... if x is going to be less than some delta, for delta being greater, no, delta in this case is going to be less than 0. Right, if x is going to be less than delta, so it's further negative, then absolute value of f of x minus m is going to be less than epsilon. So it has to be within a certain distance, within a minuscule distance of m. Our choices here are going to be arctan of x and negative pi over 2. Okay. Arctan of x is going to be greater than negative pi over 2. So arctan of x minus negative, so plus pi over 2 is going to be greater than 0. Right, so we already saw that from our drawing in here, from the graph. Negative pi over 2 is going to be this lower bound. So our arctan of x is always going to be greater than negative pi over 2, which meant that, again, arctan of x plus pi over 2 is always going to be greater than 0. So now, this means that the arctan of x plus pi over 2 must be less than epsilon. And this means that this is going to be less than epsilon minus pi over 2. Arctan of x. And that means that x is going to be less than the tangent of epsilon minus pi over 2. Again, this is part 1, where we're basically trying to say, how do we solve, how do we figure out what the relationship needs to be between delta and epsilon?
That's because video is taking center stage on Spotify, with over 300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
So we're going to choose delta to be equal to tangent of epsilon minus pi over 2. And then 2, now we do the same thing that we did on the other one. We're going to let delta equal tangent epsilon minus pi over 2. We're also going to let m be equal to negative pi over 2. And f of x is arctan of x. So then, now we say when x is less than delta, this means that x is going to be less than tangent of epsilon minus pi over 2. We take the arctan of both sides. This is going to be the arctan of x is less than epsilon minus pi over 2. Now this does work because the relationship is 1-to-1. So tangents and arctangents are one-to-one relationships. We don't have to worry about ending up with a negative value, and therefore we need to switch the sign or anything like that. Right, so this is arctan of x plus pi over 2 must be less than epsilon. Arctan of x minus negative pi over 2, just to put a fine point on it, which is less than epsilon, which this must be the absolute value, but it doesn't actually matter if it's the absolute value or not, because, again, arctan x plus pi over 2 will be greater than 0. So this is saying that anytime that x is more negative than this particular tangent function evaluation, then some delta, which is a totally arbitrary location, this relationship between epsilon and delta will produce that the distance between the arctangent function and negative pi over 2, the bottom bound, will always be less than some particular epsilon value, which again is just a constant. Right, so that proves that yes, using the epsilon delta function, using the epsilon delta proof definition, we will always end up with a a lower limit in this particular case, right? As long as x is beyond a particular value in the negative direction, then our distance between the arctangent function and this, what we call lower limit, will always be smaller than a particular amount, epsilon. Cool. I know that Stewart, in his calculus book, preferred to say that if x is beyond a particular n value, using capital N to refer to, like, you know, some constant that's just a really big number. And it might have been lowercase for horizontal and uppercase for vertical, but either way, it doesn't matter. That's the idea. For stuff like this. So I think we're going to run into the same kind of thing. If x is beyond some big n value, again, as Stewart would have it, if x is beyond some delta value, we could also say here, then we asserted that this had a limit value. So again, absolute value f of x minus m, whatever that m value is, will be less than epsilon. We already found it. We know it should be 0. So again, if we go 1, find the delta epsilon relationship, This was 2x squared minus x plus 1, I think. 2x squared minus x plus 1, yes. Over x cubed plus 4. Minus our m value was 0. All right, given sufficiently large x, then the fraction itself will be positive, so the absolute value is not necessary. 2x squared minus x plus 1 is greater than 0, and x cubed plus 4 is greater than 0. Therefore, 2x squared minus x plus 1 over x cubed plus 4 minus 0 will be greater than 0 strictly. So therefore, also therefore, 2x squared minus x plus 1 over x cubed plus 4 minus 0 is going to be less than some epsilon. How do we turn this into something that's greater than delta? Oh, yeah, this is going to be an issue. Let's see. So, hey Zach, how's it going? Yes, so I am trying to work out the oddball ones that we had here because in the GRE, this is, as always, trying to solve the question rather than actually, you know, be mathematically rigorous because they want to do it within the appropriate amount of time. I'm trying to get to the bottom of why does it work this way, and then we'll discuss why the yeah, then we'll discuss what is the fastest way to get the answer that we want. So, how do we mathematically prove that this is the answer? Then, how do we get the fast answer? I did, however, go to the, go-to answers here, back when we were talking about just, what's the limit of this particular fraction? Okay, my go-to is either we use multiplying by 1 over the largest degree term, or we go with, down here, it's equivalent to the precalculus thing. You just look at the first terms, and then what do you get from that? Now using our limit definitions. Right? If we plug stuff in, we get indeterminate forms, so we can't do this, so let's do something better. This was using a trigonometric argument, right? What do we get when we go to negative infinity for arctangent? Well, arctangent is the x value on the inside is looking for the slope, and the arctangent itself is looking for the angle. So let's work that out in terms of what we're supposed to do here. You know, have a negative slope because, sorry, tangent, right? The value of the tangent is the slope value for the terminal side of the angle. So then as we get closer and closer to vertical in the negative direction, we're getting closer and closer to either pi over 2 or 3 pi over 2, which has to be turned into negative pi over 2 because of the whole domain thing. Right, and then how do we get the limit as x goes to 0 of 1 over x? Well, guess what? That can't happen. So then we said, we didn't actually ask, but if you only do one-sided, then how do we solve that? And then we did epsilon delta, and we've been working kind of backwards from there ever since. So I'm trying to do an infinite limit, or a limit at infinity, for this particular nonsense, which I think the easiest way to do this is to say that we can come up with a no, we need to go the other direction, don't we? We need to come up with something that was inside of here. Right? Take our known value and kick it out further. So what's bigger than this? Okay, no, this works. So we need to come up with something that's bigger than the thing we're trying to play with. Okay, so actually I was correct in what I was thinking. So what's bigger is going to be just x cubed in the denominator, because now x cubed in the denominator is a larger number because our denominator is smaller. If only marginally, but still. And then in the numerator, we want something that is bigger. So, I mean, 2x squared is going to be bigger than 2x squared minus x plus 1 as x goes larger. So as x becomes more and more positive. Right, so 2x squared minus x plus 1 is going to be less than 2x squared, right, for all values of x that are greater than 1. So, yay. And then x cubed plus 4 is going to be also less than. That's not what I want. No. 1 over. Right, 1 over x cubed plus 4 needs to be less than 1 over x cubed. When does that happen? Again, these are positive, so they stay where they are. And that's going to be x cubed less than x cubed plus 4. As long as, subtract those out, 0 is less than 4. Well, good news. Right? That is always the case. So then this means that we have now, either we can leave it as 2x squared over x cubed, or have it as 2 over x. So let 2 over x be equal to delta. That's maybe, no wait, hang on. That's not what I want. Hang on.
There's more to Spotify than meets the ear. That's because video
Ah,
is taking
right.
center stage on Spotify.
Let delta be equal to, we need to solve for x.
Watching their favorite
That's what it
podcasts.
was.
With seamless switching between watching and listening.
I'm
You
okay.
can tune in anytime, anywhere.
Right,
Show us your
so
upload
this
your
is
video
going to
to
be
Spotify. Turn views into fans.
2
and
over
monetize
x
your
is
passion.
less than epsilon will become 2 over epsilon is less than x. And then we just let delta be equal to 2 over epsilon. Okay, so then part 2 is we found the relationship that works. Therefore, we now need to go through and rewrite that relationship in terms of a formal proof. Right? Let delta be equal to 2 over epsilon, comma, that is n m equals 0 and f of x be equal to 2x squared minus x plus 1 all over x cubed plus 4. So the formal proof begins here. We said that if the distance between x and, oh no, if just x is greater than delta, right, or again, x is greater than capital N, then the distance between 2x squared minus x plus 1 over x cubed plus 4 minus 0m is less than epsilon. Okay, so we say that x is going to be greater than 2 over epsilon. Right, we now let epsilon be greater than 2 over x. We say that this is going to be epsilon is greater than 2x squared over x cubed, which is going to be greater than 2x squared minus x plus 1 over x cubed plus 4. Because in both of those cases, did I do that wrong? We might have done that wrong. Right, because you can't do numerator and denominator and then take them into a... take them and put them into a ratio with each other, because then that will not necessarily work. However, we want to do something similar. Right, where does 2x squared minus x plus 1 over x cubed plus 4 have a larger value, nope, have a smaller value than 2x squared over x cubed? Okay. If we simplify, we say 0 is not going to be an answer. Right? X is far greater than 0. Then we can multiply both sides by x cubed and x cubed plus 4. And we can divide out x squared from the right-hand side, leaving just 2 up top and x on the bottom. So now we can just multiply by x and x cubed plus 4. So this is going to be 2x cubed minus x squared plus x is less than 2x cubed plus 8. Right, get rid of these. And we make this 0 is less than. When is x squared minus x plus 8 going to be greater than 0? I think maybe always. Because that c value is very big. Right? Negative b, no, b squared. B squared is negative 1 squared is 1 minus 4 a c 1 and 8. So this is going to be yeah, 1 minus 32. So we get a negative 31, which means that for the sake of completeness, we need to show that it is always, because it could, in theory, be never. So plug in a 1 as the value. 2 minus 1 plus 1 over 1 plus 4 is less than 2 times 1 over 1. Right, so 2 minus 1 plus 1 is 2 over 1 plus 4 is going to be 5 is less than 2. True. Which means that it is in fact always going to be less than the other. So yeah, we're good. Actually, we did pick one, even if my method was not 100% accurate. Right, let's destroy the evidence. Right. So, even though the method was not sound, the idea was correct. 2x squared over x cubed is always going to be greater than 2x squared minus x plus 1 over x cubed plus 4, and then, because of that, we can simplify this so that our delta becomes 2 over epsilon. Okay. So this is true. Right? Our 2 over x is always greater, which is what this sign is showing here. Always greater than the other. Okay, and when x is significantly greater than 0, it is also true that 2x squared minus x plus 1 over x cubed plus 4 is going to also be greater than 0. So therefore, we know that the absolute value of 2x squared minus x plus 1 over x cubed plus 4 minus 0 is going to be, reading it the other way, less than epsilon. QED and all that. Right, so no matter how big our delta gets, we will always be able to find an epsilon that is within a minuscule distance from 0. Meaning that this thing does, in fact, converge to 0. It has a limit as x goes to infinity. F of x is going to approach 0. That's what we were looking for, right? Yeah. X goes to infinity. What does that thing do? Yeah. Cool. Alright, last one. X squared plus 4. We're going to do the same thing here. So, number 1, again, the relationship that we want to show is that for some x value which is greater than a particular delta, capital N, whatever you want, then the 2x squared minus x plus 1 over x squared plus, is that one 4? Yeah, x squared plus 4 is always going to have a distance to, well, we argued in the previous one that it was 2. Of less than epsilon. Alright, as x gets really big, this thing should go to 2. And that was our argument from above. Ads are going to start in 5 minutes. And we're going to take a quick break. And then come in for, what, one last? Oh no, we gotta talk about continuity. Woo! Right, so step 1, find the relationship that exists between delta and epsilon. So absolute value 2x squared minus x plus 1 speedrun over x squared plus 4 minus 2 is going to be less than epsilon. So in this one we could multiply our 2 by x squared plus 4 over x squared plus 4. Works for me. Right, 2x squared minus x plus 1 minus parentheses 2x squared plus 8 over x squared plus 4. Slightly awkward. So this is going to get rid of our 2x squared, and then the negative is going to make that negative 8 plus 1 is going to be negative 7. So this is negative x minus 7 over x squared plus 4, absolute value less than epsilon. So, as x goes to infinity, we know that negative parentheses x plus 7 is going to go to negative infinity. So we take the absolute value of negative x plus 7, and that's going to be equal to x plus 7. Again, x is going to positive infinity, so x is greater than 0. That's going to hold to be true. That's inconvenient. So that means that x plus 7 over x squared plus 4 is going to be less than epsilon. That's not particularly nice.
There's more to Spotify than meets the ear. That's because video is taking center stage.
And now we're going to get entanglement between the epsilon and our x's.
With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify. Turn views into fans.
Righto. Let's take that 3-minute break now. We'll think about it, and we'll come back. So thank you everybody for coming in, and be back in 3.
Music is Shame. Shame. Shame.
Ahoy, everybody! Yeah. Well, I'm also sorry, not sorry. All right, here we go. I was just coming back to also tell y'all that decided to self-impose a diet today. And before everybody's like, oh no, diet. Yeah, it's actually been going pretty well, because basically last few days I've had like just like a bowl of oatmeal with some other stuff in it for breakfast, and then like well, lunch is usually leftovers, but today I was like, well, I don't have any leftovers because my spouse took all of them. So then I'm like, all right, well, I will, we just went shopping, and I grabbed like a huge bag of kale and various things from all over that my son might actually like to eat, because he doesn't like to eat a lot. And so I took like one whole bell pepper that he had intended on eating himself and took it for my lunch, went and grabbed a handful of kale, and then like a hunk of the bread that we usually get with foil. And I was like, that's my lunch. And, you know, decently healthy at least. Alright. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, yep, 17, 18, 19, and 20. Oh. I've been stalling out pretty close to 15 for basically my entire life. So, that is Exploding Kittens, yep. Let's see. Oh, you can't see Exploding Kittens, actually. Got Exploding Kittens here. Bananagrams, always one of the favorites. Our kids don't like playing against us because we're too loquacious. Let's see what else. Zombie Kittens, because my son is absolutely obsessed with it. Sleeping Queens is actually a pretty good one for like travel. So this has worked pretty well for when we're on the train. Oh, King Domino, excellent for pretty much all ages. It says 8 plus. Our son was playing it at 6. He loved it. It's kind of like, you know, depends. Let's see. What were you looking at? Ah, you were probably looking at Set. Right here. Perennial favorite for all mathematicians. I picked up a new one, which I have yet to actually do anything with, but it's called Compile, which is like you build a computer essentially in front of you, and then you have to go and compile your code and attack, I think, attack another hardware setup that somebody else has. This was at the so there is a River Aire that runs through Yorkshire, and this was at the Air Con. So I think it's every year they have a massive board game convention in Harrogate, and it's called AirCon. This year there was a metagame. I think I got rid of it probably, but the booklet that had the schedule of events also had a RPG that was in it that said, like, you know, you could be one of the following races, roll a d6, and it's, you know, you're a goblin, you're an orc, whatever, and then roll a d6 for this particular event, and, like, you know, at this time on this date you roll this die, and then this is the thing that's happening. You know, the air conditioning is set too low, the air con is set too low, and now you have to go fix it. So you have to find a particular booth and then, like, roll a particular value. If it succeeds, then you get a point, and if it fails, then you have to, like, I don't know if it was do something social with other people around you so that you succeed as a group. But there was a bunch of stuff. It was kind of funny. These are Eclipse. This is a fabulous game and an alternative to Twilight Imperium. If you like Twilight Imperium, you probably will love Eclipse because it doesn't last as long. Splendor is a wonderful game. This is the expansion for it, but Splendor, you get these really awesome gemstone tokens, which are really chunky. I love them. So the gemstone tokens are like these heavy plastic, and here, listen. So you get these nice tokens, and they're like heavy poker chips basically, and you try to set up an engine in order to you know, game engine, in order to produce, like, mine gemstones and then sell them in order to get more stuff, in order to get more mines, more different kinds of gemstones, things like that. Let's see. That one is Unlock. It's a great, like, alternative to escape rooms. It's just like you do an escape room with a bunch of cards. So it's good for, I'd say, younger kids. Not younger, but it says 10 plus. That's probably accurate. Our 8-year-old doesn't really like it. That one over there is Pickwits. That's another of his favorites. Most of us are getting kind of sick of it, but alert you when Pen goes live. Yeah, so anyway. There's all sorts of good stuff. We we had friends of ours who had shelves that are like that. So it's four. Yeah, four in the top. So 5 sections where you can just stick board games. They had some that ran basically the entire length of our room here. There we go. Basically the entire length of our room, and then also along another like sidewall. Program your robotics kit to just do your math homework for you. Yeah, the problem is that it ends up being harder than just doing your math homework. I mean, at least you will know how to program it to tell you when pen goes live. That's a almost trivial type thing. You just like hook it into the API, right? Yeah, Penn couldn't actually see Exploding Kittens because that was actually behind something. But there are multiple games which look very similar to it. So I'll give you that one. So the guy who also had like the ridiculous number of games there said when he was in college at Georgia Tech, he and his roommates had like a 2-room suite, and so they cleared out the front room, took all the furniture and put it into the back room, lofted their beds and all that good stuff, and then they set out Axis and Allies. The whole thing. And like whenever they weren't doing something else, they were playing Axis and Allies. They did the entire Napoleonic Wars campaign at once. Oh no. So they did, yeah, they did the entire Napoleonic Wars campaign. It took them, he said it took them the better part of their entire semester to do it. Done by Christmas, unlike the real war. And he was like, yeah, I'm kind of done with this game now. He said he and his girlfriend also had done a really intense game of Twilight Struggle. And it was like a 4 or 5 hour game, something like that. And they kept like dancing around the end condition. They just weren't able to cross the line. And he was about to win on his next turn, and she knew it. And she suddenly realized what she had to do, scored 3 points in a single turn, which is almost impossible. Immediately burst into tears, ran from the room, and they have never played it since. She said it was just such a stressful game entirely that like she will never play it again. And meanwhile he's sitting there going, what just happened? Oh, yeah.
You can download your music at higher quality, listen to songs ad-free, and play them in any order. Tap the banner to learn more.
So yeah, I've been really good with my quote-unquote diet today. Nothing sweet that isn't fruit. Which by itself can be too much. You know, can be too much sugar. But the kind of sugar it is, at least, isn't like also caked in fat. So, you know, slightly better for you, and it's got fiber in it. So. So, day one's a success. Handful of kale as part of my lunch. Another handful of kale into our dinner that went to all of us. And like, kale is a really bitter vegetable, but when it's good, it's like really good. Even if it's bitter, it's alright. You cook it, it's a little bit better. Okay. So... Right, we can do this. This has to be done the same way that we did the other one, which is to say that we need to take this entire thing, shift it over, and find something that is always going to be greater than that. And we want something, like, simple. So x plus 7 over x squared plus 4, when is this going to be less than, you know, 1 over x? If we just take the lead coefficients, drop the rest of that stuff off. Is this going to be actually less than this? This is going to be x squared plus 7x less than x squared plus 4. So, no. This will in fact fail because we are going to need x to be less than something. Gonna be an all-nighter. Aw. That's alright. I understand. Yep, as is usually the case, right? Alright, so we want something that is going to be decreasing. We want it to be preferably monotonic 1-to-1. Oh. How about plus 2? So that turns this into 2x plus 1 on the right. Right, so x plus 7 over x squared plus 4 is less than 2x plus 1 over x. Okay, shift it up. And that should, in theory, always be greater than the other one. Let's just double check. So this is x squared. Ooh. I don't like that very much, but alright, let's see what happens. Well, hang on. Let's have this be right, so it can't be just x over x squared. So we're seeing that going with x plus 7, decreasing it down to just x, is too much of a leap. But what about 2x over x squared? No. We need this to be right, if it's just 2 over x, where does that put us? X squared plus 7x less than 2x squared plus 8. That's going to be 0 less than x squared minus 7x plus 8. Is that factorable? No. But it does give us two answers and right, for x much greater than 0, x squared minus 7x plus 8 is greater than 0. Right, so there are finite values for this. Minus 7x moves us that way, so we're going to be like that. Yeah. Right, so for positive enough x values, then this parabola is always going to end up being in the positive zone, which means that this thing can actually work here. Right, so we can actually use just that function, 2x over x squared, to be an analog for x plus 7 over x squared plus 4. Right, we actually want this to be close to 0. So this was okay. Yeah, this is fine. Okay, then 2 over x is less than epsilon, which means that it's the exact same thing we did before. X must be greater than 2 over epsilon, which again, we're just going to say, like, let delta be equal to 2 over epsilon. And then we start in with number 2. So we do the actual delta epsilon proof, which says that if x is greater than delta, then the distance between f of x and that particular m value will be less than epsilon. We're letting delta be equal to 2 over epsilon. M being equal to 2, and f of x being equal to that nonsense up there. 2x squared minus x plus 1 over x squared plus 4. Yep. Okay, so Then, when we actually do this, we're going to start with x is greater than 2 over epsilon, which means that epsilon is greater than 2 over x, since epsilon and x are both greater than 0. Okay, epsilon is greater than absolute value 2 over x. Again, since x is greater than 0, that doesn't change anything. So that's perfectly fine. It's greater than absolute value of 2x over x squared, doesn't change anything, which is itself greater than absolute value 2x. Hang on. X plus 7 over x squared plus 4. Which seems completely random, but that's okay. For values of x much greater than 0. Again, we have numbers for it. It's just yeah, we have numbers for it, but we'll just hand wave it for now. Seriously though, if you want to, you plug that into Desmos or what have you and look at the graphs and make sure that I'm not just lying. Right, 2 over x compared to x plus 7 over x squared plus 4. Oops, 4. Right. So we have an intersection point where the blue graph becomes larger at 1.434-ish, and then it becomes smaller again at 5.56. So, interesting. No, that was right. Okay, I did draw the graph correctly. Right, both of our zeros are in the positive region. Sooner you finish your programming courses, the sooner you can get started working on a project. True. Very true. Okay. So again, as long as we're over 5.56, then we end up with right, 22, actually, let's just bump data. All right, 20,100.0001. Right, 20,100. Blue is at 0.00005, so it's less. So 2 over x, or 2x over x squared, is greater than the other one. Right. So then, by some miracle, not really, this then can become 2x squared minus 2x squared minus x plus 2x plus 1 minus 8 all over x squared plus 4. Right, this is just a matter of bookkeeping and keeping track of whatever we did up there in reverse. So epsilon is greater than absolute value of 2x squared minus x plus 1 minus 2x squared plus 2x minus 8 over x squared plus 4. Oh, something's not right. Oh, that's what it was. Yep, okay. We can't do that yet. Right, we're off by a bit. This is also equal to, right, negative parentheses x plus 7
There's more to Spotify than meets the ear.
over
That's because video is taking
that
center
stuff.
stage on Spotify, with over 300,000 video
Right,
shows
and absolute value is the same whether the numerator or denominator, the whole fraction entirely, is positive or negative.
anytime, anywhere.
The absolute value of that thing, we always end up with the exact same stuff.
Turn views into fans and monetize your passion.
Okay, and that means that, again, now we can split this into 2x squared minus 2x squared, a negative x, and a plus 1 negative 8 gets us the minus 7. Okay, all over x squared plus 4. That means that, yet again, epsilon less than absolute value 2x squared minus x plus 1 minus minus parentheses, and in fact take a 2 out, minus 2 parentheses x squared plus 4 all over x squared plus 4. That means that we now have epsilon is greater than absolute value of 2x squared minus x plus 1 over x squared plus 4 minus 2 times x squared plus 4 over x squared plus 4. So epsilon is greater than absolute value 2x squared minus x plus 1 over x squared plus 4, all minus 2. It worked! No one said surprisingly, because, again, this is not surprising, it's just using the exact same thing we were doing earlier to try and, like, simplify everything, to now expand it in some direction that, if you just saw this, it looks weird. Like, why would you do it that way? Well, it's because we already know what the endpoint is. And we have to expand it in such a way that it looks kind of weird. But when you actually do it, when you do it from reverse, you simplify from a much more complicated expression. That's just the natural progression for how you get back up to what we would call the top in this argument. So we want epsilon is greater than 2 over x. But we had no idea how to get there, right? We needed our delta to be 2 over epsilon. We don't know how to get there. So what do? Again, we start with the conclusion, this then part, and then we just say, if we were to do algebra, what do we get? Right? Just simplify it all the way down. 2 over epsilon is less than x. Cool. Then we're going to start with that assumption and work our way backwards when we do the actual proof. So anybody who looked at epsilon delta proofs and was like, how in the hell did we do this? Or why are we doing this backwards and then forwards? Like, why are we doing it twice? We're not doing it twice. The first one is to investigate what the relationship between delta and epsilon needs to be, and then the second one is formally showing the proof of how we get from if x is greater than delta, then the distance between f of x and m is going to be less than epsilon. And this one looks different because this is not the same as your normal Calc 1 stuff. This one right here is actually telling us the limit definition of an, was it limit at infinity? Yeah, limit at infinity. We're actually going to get a finite value. So, limit at infinity to get a finite value, we're saying that as long as x is above a certain level, above a certain value, then our y value, our function value, has to be within a certain distance of the limit that we're looking for. In this case, we knew it to be 2, y equals 2 from before, or just from looking at it, right? 2x squared over x squared, you're going to get 2. And anyway, we got this thing here, so we got the negative x minus 7, which is telling us here, right, you could take out the negative, and it's going to be absolute value x plus 7, since we know that x is going to positive infinity. Alright, if anybody has any questions, let me know, because I can stop whenever I want. Everybody talks about meth addictions. They don't talk about math addictions. All right. If nobody else goes on to anything else, we'll talk about continuity. Right, functions will continue over particular intervals without interruption. So the interruptions we generally call discontinuities. Right, and if we were to just draw a random function, right, how do we make this discontinuous? How do we make this function not continue, or how do we interrupt it? Well, one example would be if we just have it not exist. Right, so we'll say like this is going to be our A, and this is going to be our B. Right, so right, type 1 just doesn't exist. So in order to be continuous, that one's real easy. right? So it must exist everywhere on A to B, right? Fair enough. Interruption type 2. A jump discontinuity. So, for example, thank you so much, Spotify, for coming up with Raven and Crane in the air. When we're talking about jump discontinuities. Somebody clip that. Alright, so we get a jump discontinuity like this. And so the problem here is that our two sides of the function are pointing to two completely different locations, right? As we're approaching the same x value. Oh. That's not gonna work. Well. Alright, so in order to be continuous, f of x must also have the same values of its one-sided limits on A to B. Alright, we'll do formal language for that in a second. And interruption type 3. Right, if it exists everywhere along that interval, and there are no jump discontinuities, like, for instance, everywhere we look, they're pointing to the same location everywhere along that function, right? The other one we can have is a... I don't know what to call it exactly, like improper fill? So what's going to happen here is that we end up having the exact same thing we were talking about with number 1. We've got an empty hole in that location, but then it's filled by some other point. Right? So it exists, right? The function has value everywhere along its entire domain, or within this particular interval. It doesn't have a jump discontinuity because everywhere you look, when you come at it from both sides, it's always pointing to the exact same location from the left and from the right. Okay? But problem here is that that improper fill is not right, not in the same location. The point is not in the same location as every single one of our limit values.
There's more to Spotify than meets the ear. That's because video is taking center stage on Spotify. Over 300,000
right, have the same limit values as the actual function value everywhere on AB.
between watching and listening. You can tune in anytime.
So what does that mean? Well, we said that it must exist.
Turn views into fans.
So
Monetize your passion.
1 f at x exists everywhere on x belonging to A to B. Two, the limit as x approaches some value c from the left of f of x must be the same as the limit value as x approaches c from the right of f of x. They must be pointing to the same location. And 3, the limit as x approaches c from the negative side of f of x equals the limit as x approaches c from the right at f of x must also be equal to f at c, the particular location we're talking about at any particular value between A to B. Right, and in fact, we can take this everywhere on A to B, and we could just stick it at the end, because it has to be true for all of these. Right, must be true for all x on A to B every single time. So, all function values f of x must exist, and the limit values from the left and the limit values from the right need to be pointing to the same value every single point, and those limit values need to be pointing to the actual function value, the point that exists f at c, every single point on A to B, wherever that is. If you could say all three of those, then you have continuity over whatever interval it is. Alright, so the stereotypical question that you're going to be asked is something like, for the function f of x is equal to piecewise x cubed minus 8 over x minus 2 when x is not 2, and k when x is 2. Right? What value of k makes f continuous? right? So what we're doing here is we're saying that the limit as x approaches 2 from either the left or the right, and in fact we could just say it's just the limit as x approaches 2 because they have to be the same. Okay, the limit as x approaches 2 of x cubed minus 8 over x minus 2 must be equal to f at 2, which in this particular case is k. Not some other weirder function of k, so that's actually nice. Okay, now this is indeterminate because we now have a 0 divided by a 0. Right, and because it's indeterminate, we're not going to be able to figure out what the actual value of that is. So we have to go in, and a bunch of ways you can do it. My favorite way here, because we have x cubed minus 8, is that this can become synthetic division. We know that our x value needs to be 2. And this is x cubed plus 0x squared plus 0x's minus 8. What do we get when we actually perform the division? We get 1, multiply is 2, add is 2, multiply is 4, add is 4, multiply is 8, add is 0. Cool. So it is x squared plus 2x plus 4, which is a constant. So we want to know, what is the limit as x approaches 2 of x squared plus 2x plus 4? That must equal k. Must be equal to k because that is f at 2. So here, this is nice. We could just plug it in now. This is 2 squared plus 2 times 2 plus 4 is equal to k. So k must be, this is going to be 4, this is also going to be 4, and this is also going to be 4. So now we have 12. All right, it is just after midnight. We've been on for just over 3 hours, and we have an ad break coming. I think probably we're gonna call it here, and then raid out to. Let's see, Don Factorial's doing DayZ. Do we have educational content still on? Rhacodactylus, I know Zach rated earlier. Phobos is on. Yep. Oh, thanks, Pen. We came to the conclusion at basically the same time. All right. Let's head on over and see Phobos stream. Hope you all are having a good evening. We will probably be back tomorrow because Elite Dangerous dropped a new ship, and it is going to help us out with space trucking, like, seriously. So, may do some of that tomorrow. Depends on how we're feeling and whatever else we feel like. So, I will see you probably tomorrow. If not, we'll come back on Friday and do Against the Storm, and try to push more toward the gold seal. So, have a good night, everybody, and we'll head on over there, hang out with Phobos, and looks like Walfawaros, and Color Cone, and Coffee and Trance are all over there. Awesome. Alright, here we go. Good night, everybody. My name is Obi-Wan Pez. This is N Simplex Pachinko. Catch you next time.